In this video, we are going to prove the theorem that z adjoin x, the ring of polynomials over the integers, is a unique factorization domain. So just to recap, in the last video we showed that every polynomial in Zx does factor into irreducibles in some way. In this video we will prove that that factorization into irreducibles is unique up to order of the irreducibles and associates. So we will show that if f of x in z adjoin x is non-zero, and is written in factored form in two different ways. Okay, so f of x is expressed as a product of irreducibles in two different ways. Let's just say two ways because they really won't be different. Then the two lists of irreducibles must be the same up to order and associates. And just so that we can keep this in mind throughout the proof, so what do we mean by associates in this case? In z adjoin x, the only units are 1 and -1. So associates will really just mean opposites of each other or the same. All right, and with that, let's begin the proof. So one thing I'm going to do here is I'm going to use a strategy similar to what I used in the last video, which is I'm going to consider numerical factors, that is polynomials of degree 0, and polynomials of degree greater than 0 separately. All right, so let's suppose f of x is equal to c1 through ck times p1 of x through pm of x, and is also equal to d1 through dl times q1 of x up through qn of x. Let's suppose these are two irreducible factorizations of f. And as always, I don't mean that the factorizations themselves are irreducible, I mean factorizations into irreducibles. So in other words, all of the c's through ck and all of the d's through dl, these are all irreducible integers. They could be negative, but aside from that, you should think of them as being prime numbers. So like 2, 3, -5, -11, whatever. Okay, so those are integers, and all the p's and q's, p1 of x, these are all irreducible polynomials of degree greater than 0. And one thing that we can determine from that, if they are irreducible polynomials of degree greater than 0, they have to have content 1, every single one of them. So they're all primitive. Because if they weren't primitive, then there would be a prime factor I could take out, and that prime factor would be a non-unit, therefore that polynomial would be irreducible. Okay, so I've got f of x split up into prime, all those integers, and then primitive, and all these primitives are furthermore irreducible, and same with the d's and the q's. All right, there's a lot of table setting here, but you'll actually find out that it's required. Okay, so anyway, so now let's consider what we have here. We have this product of all the c's. We have the product of all the d's over here, and those are both, let's keep in mind, these are both parts of f of x, the same polynomial f of x. And then here I have p1 through pm, I have q1 through qn, and those are both parts of the same polynomial f of x. Furthermore, the product of all these is primitive, because I know that the product of any two primitive polynomials is primitive. And same here. I mean, I said any two polynomials, but really I could stick another polynomial on that's primitive, and that product will still be primitive and just keep inducting. So the product of P1 through Pm, primitive. The product of Q1 through Qn is also primitive, which means the content of each of these is 1. The blue parts, that is. So that's great, because I also know what the content of all the red stuff is. The content of that is, it looks like it's going to be the product of all these numbers, C1 through CK. And it almost is. It's really the absolute value of that, because if I have just a C1 there, no other C's, and that C1 is -3, I wouldn't say that the content of that is -3. I would say the content is 3. Same with all of these. The content is going to be D1 through DL, absolute value of the product. And so, because I know that content is multiplicative for integer polynomials, so the content of f of x is equal to, well, on the left side, it's equal to the product of C1 through CK, absolute value, times 1. That's the content of the product of all the p's. But it's also equal to the product of D1 through, sorry about that, that's DL, absolute value times 1. And because those are the content of the same polynomial, that means that these numbers are exactly the same. The absolute values, that is, are the same. It is not necessarily true that the product of all the C's is equal to the product of all the D's. They could be opposites of each other, and I can't remove that by being nitpicky about how I define f of x. I mean, I guess I could, but then I'd be avoiding the issue of showing that any two possible factorizations are the same. I really need to allow C's and D's to be negative if they want to be negative. But what I can say is that we know that this is an integer. The absolute value is an integer. It is a positive integer with its own unique prime factorization. And that's important because that means that even though the C's don't have to exactly equal the D's, we do have to see the same prime factorization here. I mean, if I see C1 equals -3, for example, that doesn't mean there needs to be a -3 over here, but there had better be a 3 or a -3 somewhere in there. So this means the list C1 through CK and the list D1 through DL. And I'm using the word list and not set very intentionally here because sets really don't have repeated elements, but lists can. So the list of all the C's and the list of all the D's must be identical up to order and associates. And here I'm leveraging the fact that the integers are known to have unique prime factorization. So that means that even if this is the opposite of the product of all the D's, then, well, I could just say, okay, stick on a -1 here. Then they're the same positive integer, or the same negative integer, but let's make them both be positive. And then once they're the same positive integer, I know I have to have the same primes represented here as here. They may be in a different order. Some of the primes may be negatives here, or maybe negatives here. But ignoring the negatives, they'll be the same list. Okay, so that means that I've already sort of halfway proven this theorem. Let's just go back and look at what we were trying to do. We said suppose f of x is equal to a product of irreducibles this way and a product of irreducibles this way. Then all of those irreducibles have to be the same up to order and associates. And what I've shown now is that the numerical ones, the ones of degree 0, do have to be the same up to order and associates, including the fact, I didn't say this before, but including the fact that k has to equal L. That has to be true as well. Otherwise, we violated unique prime factorization for the integers. Okay, so now we are halfway done, or at least I like to think that we are halfway done. I'm not sure whether the other half is easier or harder, but now we're going to work on the primitive parts. All right, so now we'll show that factorization into irreducibles of a primitive polynomial in Zx is unique. And again, I'm posing this as a separate task, kind of like I did in the last video for the existence of factorization theorem, because I'm going to want to do this part by induction. And I've already set f of x here, like I've already declared f of x. I've said it's equal to this, it's equal to this. So I can't let f of x vary in the middle of this argument. So instead, I'm going to talk about some other primitive polynomials, which hopefully I will find decent names for. And we will show that factorization into irreducibles of those is unique. All right, so let's just zoom down here, set that aside. All right. You might think that we are going to prove this by induction on the degree of the polynomial like we did in the last video. And I actually recorded 7 minutes of video thinking that I was going to do that, but I'm actually not going to do that. This is not a proof that we are going to do by induction. I guess you could, nobody's stopping you, but I think we can do without induction actually. So we're just going to show that a factorization of a primitive polynomial in Zx is unique. So to do that, we're going to let it have two factorizations. Suppose P of x is in Z of x and is unique, or not unique, is primitive. And let's let it have two factorizations. So P of x equals a1 of x through a m of x. And I realize I'm reusing m and n. I apologize. I was running out of good letters for integers. So let's suppose these are irreducible factorizations of P of x in Z adjoint x. So in other words, each of these polynomials, a sub I, b sub j, is a irreducible polynomial in Zx. All right, so first of all, I claim there are no constants here. None of the a's and b's are constant. Okay, why is that? If they were, if one was, I mean, let's just say a1 of x, because that's as good as any of the other ones, then, well, being an irreducible, it would have to be a prime number, or a negative of a prime number. So it would equal plus or minus p for some prime p. Some prime number p. Okay, but that would be a problem because then p would divide the content of p of x. I'm realizing now it's kind of ridiculous to use p for a prime and also use p for polynomial. Just bear with me. This is an argument that's going to be over very quickly. So the content of p of x is not 1 because it's got that constant factor lurking inside of it there coming from a1 of x. All right, so this is a contradiction. All right, so none of these a's and b's are constant. All right, end of claim. All right, so now that means that each of the ai's and each of the bj's has to have degree greater than 0. Okay, and now if I know that they all have degree greater than 0 and they're irreducible over the integers, then they also have to be irreducible over the rationals. That's a theorem that we have. So since each ai of x, bj of x is irreducible over z, it is also irreducible over q. Okay, now you may wonder, why did I need to prove that they were non-constant to be able to say that? Because didn't we say that the theorem was if it's irreducible over z, then it's irreducible over q, and that was regardless of constant or non-constant? And the problem was there is the possibility of an irreducible turning into a unit over q. So for example, what if one of these was like a 3 or something? If one of these is a 3, that is irreducible over z. It's technically not irreducible over q because that 3 becomes a unit. So that's why I need to establish no constant factors, which is why I needed to reduce down to the primitive case. Okay, so anyway, I'm sort of burying the lead here. This is amazing because now I have this p of x. It is a polynomial in Zx, but it's also a polynomial in Qx. And now I have these two factorizations which are factorizations into irreducibles, over Q. Well, what do I know about QX? I know that QX is a principal ideal domain, therefore it is a unique factorization domain. Therefore, these factorizations have to be the same and have to have the same number of irreducibles. So, by unique factorization in QX, the AIs are the same as the BJs up to order and associates. But now this is where we need to be a little bit careful here, because associates in QX might be a little bit different from associates in ZX. Okay, so let's think about what that means. If AI of X is an associate of BJX in Q bracket X, well, Q bracket X has a lot of units. Any rational constant, non-zero constant, is a unit in QX. So that means AI of X has to equal, and let's call it Q BJ of X for some non-zero rational Q. And let's say Q is equal to R over S, where R and S are relatively prime. Because it could be any rational, I need to take into account the possibility it could be a fraction. So then, that would mean, since Q is equal to R over S, I think that means S AI of X is equal to R BJ of X. And now these, in this equation here, are both integer polynomials. I force them to be by multiplying by that denominator. So these are in Z adjoint X. And I know that AI and BJ, both of those have to be primitive. I didn't say earlier, but if I'm factoring a primitive polynomial, then the factors had better themselves be primitive. If they're not, then I'm introducing constant factors that I'm not going to have any idea what to do with here, because this has to have content 1. So this is primitive. This is primitive. I'm multiplying by R and S. That means the content of this right side has to be R, or the absolute value of R. The content of this has to be the absolute value of S. So then I'm just going to say by content, because I said a bunch of stuff I didn't write down. Absolute R has to equal absolute S. So Q, which is R over S, has to equal plus or minus 1. And now we are nearly there, because now that means that not only are these associates in QX, they also have to be associates in ZX. So when I say up to order and associates, that associateness is robust. It's robust into Z adjoint X. So wrapping up, the polynomials A1 of X through AM of X are the associates in some order of B1 of X through Bn of X. So M has to equal N, and this part of my prime factorization is unique. All right, let's zoom out. We've done a lot of work here. Wow, okay, that was a ton. So let's go back here now. Okay, so actually I didn't need to jump down and start thinking about a different primitive polynomial. I thought I was going to use induction on this part, and I think I said I was going to earlier in the video, and I ended up not using it. So I could have said the whole thing that I said about A's and B's. I could have also said about P's and Q's. All right, so what's the point? Well, the point is, so now we know the CIs and DJs are identical, up to order and associates. And now there's one more little tricky bit I have to be careful about, because down here I was talking about one primitive polynomial, which was factored in two different ways. This might be a little bit different. The product of the p's and the product of the q's don't have to be exactly the same. They could be, one of them is the opposite of the other one. In other words, this product here could be an associate of this product here. But as we've pointed out a few times now, associate just means either it's the same or it's opposite, which means I can still use this argument about prime factorization or unique factorization to get that these all have to be associates of these, just by taking the opposite of one of these so that they're equal. Let me just write down a little bit to suggest that. So we know that the CI's and DJ's are identical. We already figured that out. And P1 of x through Pm of x is equal to plus or minus Q1 of x through Qn of x. So if they're equal, the argument below applies. If they're opposites, then apply the same argument to this product, P1 of x through Pm of x, which is equal to negative Q1 of x through Qn of x. Then you have equality. Whew. Okay, so anyway, we're 22 minutes long now, but I think we have proven that factorization of a polynomial in Zx into irreducibles is unique as long as we don't care about associates or the order of the factors. Okay, that's it.